Our next speaker is Vishal Singh, who will tell us about quantifying the performance of approximate teleportation and quantum error correction via symmetric two-PPT extendibility. The floor is yours.
Thank you. Hello, everyone. That's the title of my presentation. So just a brief outline. I'm going to talk about approximate teleportation. Then we're going to look at a semi-definite program with which we can estimate the simulation error in the approximate teleportation using two PPT extendibility constraints. And we're going to use some symmetries to simplify the STP and then connect it to approximate quantum error correction. So the approximate teleportation protocol looks something like this, where Alice has to send a state to Bob, and they share a known resource state, rho A hat, B hat, and they're going to use a channel L to simulate an identity channel with this. So this overall channel N has to be as close to the identity channel as possible, and they're restricted to use only one-way LOCC communication. So L has to be a one-way LOCC channel. Only Alice can send classical information to Bob, and they both can apply local operations. And we're going to quantify the error in simulation by diamond norm. So the error is going to look like this, where A is an appending channel that appends the resource state rho, and L is the one-way LOCC channel that we're looking for. And so eventually what we want to do is optimize over all these L channels and find out what is the minimum error possible given the resource state rho. So so we want to write a semi-definite program for this, but we have a problem that it is difficult to optimize over the set of one-way LOCC channels. So to come across this problem, we find a set of channels that can be characterized by semi-definite constraints, because it is something that can be efficiently solved in classical computers. With efficiently, I mean in the dimension of the matrices and not the dimension of the qubits. So to find this set of channels, we demand that the channel be two extendable and that the extension be PPT preserving channels. So we know that two extendable channels are they contain the set of one-way LOCC channels, and so does PPT preserving channels. And so we want to look at a set that is as small as possible. And then we're going to optimize over this larger set for a relaxation of the set of one-way LOCC channels, and that will give us a lower bound on the exact simulation error. So just a reminder about diamond norm. The diamond distances between two channels is defined as follows, where you optimize over some state psi, and you just see the difference, see the trace distance between the outputs. And this can be calculated using a semi-definite program, which looks like this. And gamma n and gamma m are the Choi operators of the quantum channels, and you just need two different variables to optimize it. And so it is a semi-definite program that can be solved on a classical computer. So we want to add in two extendability and PPT conditions. So it looks something like this. So the original channel had inputs A hat, and B hat, and an output B. Now we want to extend this to another system, which is B2, and we demand that this is permutationally covariant. That means if we swap the inputs and the outputs at the same time, the channel doesn't change. So this channel remains unchanged under this action, and it can be described by a semi-definite constraint. The second condition is that it should be non-signaling. That means if we trace out B2, the output from B2, that means we get the original channel. So M is the extension and L is the original channel that we were looking for. So what it means is that B1 or B2, they cannot signal back because we require that the channel is a one-way LOCC. Only Alice can send classical data to Bob. And this can also be written as a semi-definite constraint. So now we look at the PPT conditions for this extension. a channel is PPT preserving if if the partial transpose on one of the systems. So this transpose is not a channel. This is just an action, and we demand that this total action is also a quantum channel, that is a completely positive and trace preserving map. And this can be written as semi-definite constraint. And we demand that the joint system of both bobs, that is also PPT preserving. So this also has to be a quantum channel, and it has a simple semi-definite constraint. So now we can write the diamond norm of the we can write the SDP for the diamond norm with two PPT extendibility constraints. This is the original diamond norm SDP, where we have just used the Choi matrix of the identity channel, and this is the Choi operator of the joint channel, where we have appended the resource state row, and this is the Choi operator of the one-way LHC channel, or rather two PPT extendable channel that we're looking for. And these are the additional constraints. This one is the trace preserving condition, which is required for M to be a channel. This is the permutation covariance condition. This is the non-signaling condition, and these are the PPT preserving conditions. So this is the SDP that we can use to estimate the simulation error or get a lower bound on the simulation error. But the problem is that M scales very fast with the dimension of the simulation of the simulated channel, as well as the resource state. So it depends on all these systems, and it becomes very hard to solve this on a classical computer for even simulating a three-dimensional identity channel. So we can use some symmetries to simplify this SDP. We know that the identity channel has this symmetry that if Alice can apply a unitary and send the information of a unitary to Bob, and then Bob can apply the Hilbert-Schmidt conjugate of that unitary, and that channel remains invariant in this condition. Also, we know that the diamond norm is invariant under unitary action. That means if we apply some unitary channel to both the channels that we're comparing, the diamond norm doesn't change. So we apply the sandwiching action to both the channels, the identity remains the same. And what we know is this symmetrized channel or this new channel, this performs equally well as the original channel. We can average over all these unitaries, and using the convexity property of the diamond norm, we can bring the integral inside and look at the dual channel. And what we can say is that this dual channel is always going to perform equally, or it's going to perform as well or better than the original channel that we're looking for. And so that suggests that the optimal channel has to preserve this, it has to obey the symmetry, that it doesn't change in the action of twirling. So we now, to be consistent with two-PPT extendibility conditions, we look at the two extension of the twirl channel. So L was the original channel, and we apply these two unitaries. And so its extension is going to look like this. We can easily see that it follows all the conditions that we were considering. And so we can look at the action on the Choi operator of this problem. So L tilde is the twirl, is the Choi operator of the twirl channel. And if the extension of L tilde is M tilde, then this is the Choi operator of the twirl channel, and the optimal channel has to obey the symmetry that it doesn't, and the Choi operator doesn't change under the action of twirling. So this twirling can help us simplify the SDP, because you can decompose a twirl Choi operator as follows. M tilde was original Choi operator that depended on the channel, but if it is twirled, then we can get these S matrices, which are constants, and these M matrices are the only operators that depend on the original channel. So we know something about these S matrices. There are 6 of them. S plus, S minus, and S0 are orthogonal projectors, and S0 to S3 are Pauli-like matrices, where S0 acts as the identity and it preserves the commutation and anti-commutation relations. And so the final SDP depends on 6 variables, which is M plus M minus M0 to M3. And even though the number of variables are much larger, we have reduced dimension of the variables, and that gives us a computation advantage, as in the code takes much less time to run. And as you can see, it does not depend on the dimension of the simulated channel. So it would only depend on the dimension of the resource states. And here are some numericals. So we considered a resource state of this form, where with some probability P, you have the maximally entangled state. And with 1 minus P, you have a separable state. One of them is a maximally mixed. So a separable state is basically useless for teleportation. And so we compare the bounds that we get if we just use PPT preserving conditions, and if we use two-PPT extendability conditions. And we can see that for low values of P, two-PPT extendability gives a better bound than just PPT conditions. So now we're going to connect this to approximate quantum error correction. The problem of approximate error correction looks something like this: that Alice and Bob, they already have a channel N, and they're allowed to do local operations on that system, and Alice is allowed to send some classical data to Bob, and then they want to simulate an identity channel with this operation. So it's the same case. We can only use one-way LOCC channels, and we again want to quantify the simulation error using time and norm. So the final diamond norm looks like something like this, and D and E are the ones that we need to optimize over to find out what is the minimum simulated error. So it is helpful to use the language of superchannels. A superchannel is a general map that takes a quantum channel to another quantum channel, and every superchannel has a unique CPTP map associated with it. So if you consider the channel N that goes from A hat to B hat, you can apply a superchannel epsilon S that would change. So this whole thing is a new quantum channel, and it has been shown that this can be dissociated in the following form: that you apply an encoder and a decoder, and they are connected with a memory system. So if we take out the channel from the equation, what we see is that this can be rearranged into this form, where you can see this as Alice and Bob being a bipartite system, and it takes A to A hat and B to B hat. And so we call this whole operation as epsilon, which is the CPTP map that we were talking about. So for two-PPT extendable channels, we know that if epsilon S is a one-way LOCC superchannel, that is what we're looking for, then the associated CPTP map is a one-way LOCC channel. And this is the same problem that we're looking for. So what we can do is optimize over two-PPT extendable superchannels to get lower bounds on simulation error. So just as the previous case, we are going to optimize over epsilon, and it translates exactly as the problem that we considered in approximate teleportation. On top of that, the unitary invariance of identity channel also translates into the same conditions, and the diamond norm and the unitary invariance of diamond norm also imply that the dual superchannel is going to be optimal. And because of the same relation, we can deduce that the unique CPTP map, or the unique quantum channel associated with the superchannel, it is also optimal if it is equal to its dual extended channel. So epsilon is the superchannel that we're looking for, and this is the action of dualing if we consider all possible unitary. And this will be the extended map or the extended channel that relates to the twirl superchannel. And so because of the parallels with the approximate teleportation case, the SDP is almost the same with only minor differences. And it follows the same map basically. The Choi operator is again the same with the 6 systems associated with it, but it can be decomposed if it is equal to its twirl operation. If it is equal to this twirl Choi operator, and then we again have the same S matrices where, and we reduce the SDP to just 6 variables, but which are much lower in dimension. And here are some numericals that we perform. So we look at the depolarizing channel to see the difference between PPT and two-PPT extendability constraints. So we are trying to simulate a two-dimensional identity channel, but we use we look at 2 different cases. If the depolarizing channel itself is a two-dimensional depolarizing channel, or if the depolarizing channel is a three-dimensional depolarizing channel, but it is being used to simulate a two-dimensional identity channel. So if it is a two-dimensional depolarizing channel, then there is no difference between PPT and two-PPT extendability constraints. But if you use a three-dimensional depolarizing channel to simulate a qubit identity channel, then the two-PPT extendability constraints perform better than PPT extendability constraints, and they give us a tighter bound. So to summarize, we use two-PPT extendability constraints, and we obtain lower bounds on simulation error for approximate teleportation and approximate current error correction. We use the symmetries of the identity channel to significantly reduce computational cost. The symmetry of diamond norm is also included in this, but it is expected that any reasonable error criterion would obey these unitary invariance conditions. And we also find out that the two PPT extendability conditions give us stronger bounds than just PPT conditions when we are trying to simulate one-way LOCC channels. And one-way LOCC, one-way communication is the keyword because that is why we have the extra non-signaling condition. And we cannot simply say this for LOCC channels. And the future works might involve a systematic analysis of these symmetry conditions. We eventually want to go to KPPT extendability because for higher the K, the closer we are to the set of one-way LOCC channels. And we would also like to identify a class of resource states that would saturate these bounds. We know some class of resource state that does this for PPT conditions, but as we have seen, that two PPT extendability performs better for some cases. So it might also be useful to identify a class that does it for KPPT extendability. And it would also be interesting to look at other semi-definite tightening of the one-way LOCC channels that would get us closer to the actual errors. That's it. Thank you.
All right, thank you for the great talk. We have plenty of time for questions. Oh, maybe I can start with one. So I wonder if you have some understanding about how tight these bounds are compared to LCC. I mean, even through numerical cases or just any understanding.
Yeah, that is one of our next steps, that we want to find out the upper bounds and see how it compares to how tight these bounds are. But we're not there yet, and we're just going to work on it a bit more.
I see. I guess it's related to is it really worthwhile going to like KPPT extendability, something like that, right? Or
Yeah, so like two PPT extendability gives us like a slight advantage over PPT.
Yes,
So we're not sure. So like just extending this method to three PPT extendability is not something that is easily achievable, I guess, because
I see.
yeah, we don't have like a systematic framework that could do this. We had to like these symmetries and these S matrices. If you go for three-dimensional, then it's going to be a lot of math that is not very easy to do analytically, I think. So we need to find some structure to the problem that could help us get to KPPT.
I see. Okay. Yeah. I just mean the ultimate target is LCC, right? So I'm just wondering if
Yes.
you know how tight it is. Yeah. Good. Thank you. Any other questions? Yeah, I remember from your paper, you have these huge SDPs,
Oh yeah, I
right?
couldn't put them in the PPT, so
Yeah. Yeah, maybe it's a good idea to showcase them next time.
yeah, perhaps. I mean, I can say about the advantage they give. They're like, for at least when the simulated channel is two-dimensional, sorry, simulated channel is three-dimensional.
Mhm.
I'm sorry, simulated channel is two-dimensional and the resource state is two-dimensional. Then it gives an advantage of about 20 times better than the original STP that we're looking for.
Mhm.
So yeah, it should scale pretty well when we are considering high dimensional teleportation.
Mhm. Okay, I guess the talk is clear enough. So yeah, if there's not other questions, maybe we should move on or we should wait.
Yeah, I guess we should move on. All right. Thank you.
Okay, so next speaker is Shenqiang Zhao. Can you share screen?